All right, so this is the greenhouse effect, right? Let's just remind ourselves exactly what that is, right? So the sun is here. The sun is shining Roy G. Biv, right? Okay. So the sun is hot. The sun is, what, about 5,000, 6,000 kelvins, right? And so the wavelength that the sun is putting out is short, right? It's in the middle of our visible spectrum, right? About 500 and something nanometers, right? That's a short wavelength. Okay. So the sun is sending all these short wavelength waves to the Earth, and the Earth is surrounded by an atmosphere. Now, by the way, the thickness of the atmosphere is about as thick as a layer of varnish on a basketball, but nobody ever draws it that way, because how do you draw something that's that small, right? So this is our atmosphere. Here's our Earth, right? This short wavelength can go sailing right through all the greenhouse gases, okay? Because carbon dioxide and methane and those things don't block short wavelengths, right? The greenhouse gases, they block infrared, okay? So we're talking like 1,500 nanometers or so. So it's a long, long wavelengths, okay? And so the sunlight sails right through the atmosphere, even though it's got carbon dioxide and it's got methane in it, right? Okay. It hits the Earth and the Earth warms up, right? The Earth warms up. But remember, the Wien displacement law says that the maximum radiation, right? And this is on the black body curve, right? If we look at the intensity and we graph it versus wavelength, right? There's this sort of curve like this, right? And so the predominant radiation, that's what we're talking about, that comes out, is going to be long, right? Because it's going to be 2.90 E minus 3 divided by a small temperature, okay? This temperature is small, so this wavelength is big. Okay, so the sunlight shines down on the Earth because it's short wavelength, it can make it right through the atmosphere, okay? But because the Earth is only warmed up, not as hot as the sun, thankfully, right? It's not 5,000 kelvins, it's only about 300 kelvins or something like that, right? Okay, the Earth tries to send out long wavelengths, okay? These are big wavelengths. and greenhouse gases absorb those big wavelengths, okay? They absorb those big wavelengths, and this warms the atmosphere. And then I think, IV, they wanted you to say, well, it radiates in all directions. So the atmosphere is going to radiate energy that way, but it also radiates it down to the Earth. And so there it is, right? So you need to say more than just talk about the wavelengths. The sun is short wavelength light. It can sail right through the atmosphere. The atmosphere, though, because of greenhouse gases, absorbs as that long wave radiation tries to leave, the greenhouse gases absorb that. And they do that because of resonance, okay? If we look at the magnitude of it, of the resonance, and we look at the frequency, right? The carbon dioxide molecule and the methane molecule actually resonates at these frequencies that these infrared molecules are. Microwave ovens work the same way. They heat things up by resonating water and other organic molecules. I guess water is not an organic molecule. But anyway, let's not worry about that. So anyway, this is the greenhouse effect, right? So short wavelengths can get in. The Earth tries to re-radiate the energy back to space, and the greenhouse gases block that, right? Now, without the greenhouse gases, we'd be frozen. I think the equilibrium temperature is, below freezing or something like that, right? So we do need a greenhouse effect to have life on Earth. It's just that too much is going to change the climate. There's a direct correlation between the carbon dioxide level and the temperature of the Earth. But anyway, so that's the greenhouse effect, right? And so the typical problem, right, is that we've got, sunlight comes in, right? And then maybe the Earth's atmosphere has an albedo. I'm just going to make something up here. I don't even know, 0.23, right? It's a number between 0 and 1, right? Which means it's going to reflect 23% of the radiation, right? So 23% just reflects off into space. 77% goes down to the Earth's surface. So here's our Earth's surface, right? like this, right? And then there is, so let's say, let's make an even number. Let's make it 0.20, right? Let's say that we've got 1,000 watts per square meter coming in, right? Okay. And let's make this, make it absorb 80%, right? Just use some even numbers here, okay? So now we've got 1,000 comes in. Well, if we block 20% into space, right? That means we're 200 watts per square meter reflects off into space, and the Earth is now absorbing 800 watts per square meter, right? Well, remember, there's this discrepancy, right? From the sun's point of view, the Earth looks like a big circle. It looks circular. It only sees the front half, right? So the Earth is absorbing over pi r squared, right? But the Earth itself is really, if we look at it from the side, right, it's really this sphere. And the area of a sphere is 4 pi r squared, right? And so this pi r squared is spread out over 4 pi r squared, right? So this 800 watts per square meter is spread out over 4 times the area over which it's absorbing it, right? So that means that on average, the Earth is absorbing, on average, on over its whole body, about 200 watts per square meter, right? And I get that by just going 800 times pi r squared, doesn't matter what r is, divided by 4 pi r squared, right? And I get 200 watts per square meter. And that is what's going to be in equilibrium with space, right? If the Earth is absorbing power at a rate faster than it's sending it into space, the temperature rises until it actually absorbs and radiates at the same rate on average over its whole surface area, right? You did these, I think, last year. Okay. So then you can set up an equation like this, right? Power radiated per unit area, right? This is just our intensity, right? And so the power is going to be sigma temperature to the fourth. And then notice that there'd be an emissivity in here too, right? And I've never seen them use anything other than 1, but if they give you an emissivity, use whatever they tell you, okay? So we would take that 200 watts per square meter, right? And then say that equals sigma, which is what, 5.67 E minus 8, right? Times temperature to the fourth. And then you can solve for this, right? Take this, divide by this, raise it to the 1/4 power, right? Okay. So that's the greenhouse effect. And I don't know if they've changed that, but I'm guessing that it's the same sorts of problems are still on there. So anyway. Where am I there?